Once again, I want to say a big welcome to everybody. And we are continuing on the regression diagnostics. Can somebody remind me some of the regression diagnostics we have looked at so far? Who can remind us of some of the diagnostics we have examined by this far? Yes, let me start with Christina. We have looked at a number of diagnostics, a number of things you should check to ensure that your regression model is done properly. Can you tell me one of the things you got to check, one of the assumptions you got to check whether it's met? Yep. Beatrice. Beatrice. I asked the question that what are some of the assumptions that we have learned that shows that, that must be tested before you do. And I asked the question, so Beatrice, give me one, Christina, give me one. Omani, give me one. And Sheriff, give me one. Sheriff, are you here?
Yes, please, I'm here. I'm here, please. Yeah.
You don't know the assumptions of regression that you have learned?
I think maybe linearity, looking at dependent, independent variable, they are using the scatter plot, whether it's linear or non-linear. So maybe linearity.
You are talking like you don't know what you're saying. Maybe you are using maybe. At this level, you are using maybe.
sorry about that.
What is the maybe about? You don't know, even though we have even learned. You didn't know before you came to school, but now we've learned. You are still telling me maybe.
All right, sorry, sir. So
what is the sorry? Stop the sorry and tell me the answer.
The assumption is to confirm whether there is linearity between the dependent and independent, variables, and so that will be tested using the scatter plot. That's one assumption that I know.
Laura, give me another. Go ahead and give me another. You don't hello. Don't worry about the hello though. Francisca, give me one.
Hello, Doc. Please, there's supposed to be zero covariance.
Between what and what?
Between the error term and the X.
Okay. Is this coming from your head?
Yeah, I've been reading it. So for the assumptions, I know them, but just sometimes it's difficult to do the calculation.
There's no calculation with assumptions. It's just a matter of knowing them. Okay, zero covariance. Godwell, give me one.
Okay, Doc, normality test.
Normality. Stephen, give me one.
No, please, the multicollinearity test.
Multicollinearity. You see, those who have learned, when you ask them, they don't even blink. They don't do because they've learned. And I know them, that's why I call them last. Okay. At this stage, you should know the assumptions of regression. Okay. One of the assumptions of regression is that there must not be heteroskedasticity. In other words, there must be homoskedasticity. And homoskedasticity has to do with the residuals. And in order to understand it, I'm just going to remind you of what the residuals are. The residuals are the leftovers after determining the relationship between the X and the Y. It doesn't matter how many the X's are. Any other thing that is not part of the X, the independent variables, it is contained in the residuals. As you can see here, the scatter plot shows gaps. Each of these data points show gaps between the point and the line. The distance between the data point and the line is a residual. The residuals or the errors are positive when the plot is above. They are negative when the plot is below. So the gap becomes a negative gap, whereas the ones on the top becomes a positive gap. These gaps are the residuals. So the residual shows you the observed value of the dependent variable and then the predicted or the actual value. The observed value or the fitted value. So this is where the Y is supposed to be, and yet this is where it is in a negative fashion below. The line is the line of the best fit that shows the average distance in the data set. Okay, so those residuals, let's now look at the residuals properly. These are the residuals. So this is a predicted value against the residuals. You can see, I told you that the residuals can be positive or can be negative. So you can see that the way these lines have been drawn, they have been drawn in such a way that some of the residual plot, together with the predicted values, some of them can be in a negative corner or in a positive corner. Anything below the zero is negative. Anything above the zero is positive. Now, the red lines that have been drawn shows that the nature or the pattern in which the residuals are exhibiting. The pattern. Okay. What is the nature or the pattern of the residuals? That is a question that you want to find out. What is the nature? What is a pattern? Is there a pattern? Is there a pattern being shown? And we are going to look at that. And when there is a pattern, what does that tell you? Does that show homoskedasticity or heteroskedasticity? And that is what we are going to look at today. When there is a pattern in the errors, is that good or bad? When there's a pattern, is that good or bad? And when you look at this, you will know what I've. So for example, the first one here, you can see that there is an increasing trend of the errors. So it starts from the bottom and it's increasing as we move further away from, to the right. So in other words, as the predicted home price is increasing, the errors are increasing. Unlike this one, it is falling. Unlike this one, it is silent. Okay, now look at this one too. Again, you can see that the errors are increasing in this blue section here. But if you look at the red section here, the errors are constant. Okay, the line will tell you that the gaps shows constancy. But then this one will tell you that the gaps is widening as you move further away. This blue one is heteroskedasticity. This red one is homoskedasticity. Now, let's remind ourselves mathematically of what the regression model usually is. This is a regression model, okay, which is showing you your dependent variable. So you have your dependent variable here, and then you have your independent variables, each one with their beta parameters. And then finally, the residual, which is error. Okay. When we talk about heteroskedasticity, in fact, heteroskedasticity appears to be the longest word in econometrics. In the world of econometrics, the longest word I've come across is and it is actually heteroskedasticity. It comes from the Greek word hetero. Hetero means different. So sometimes we talk about heterogeneity, you know, heterogeneous society, different society. And then Skedastic actually shows spread. And this spread is measured usually by the standard deviation or the variance. And the way you interpret the heteroskedasticity is that the variance of the error given the independent variable is not constant. In other words, the variance of the error changes across observations. Now, when you look at the one that was the red one, the variance of the errors, the net variance was not changing, it was constant. But in heteroskedasticity, the variance of the errors changes as the observations, are changing. And what brings about heteroskedasticity? When you omit some variables. Okay. So let's say that you have variable like x1, you have variable like x2. Okay. There was supposed to be a variable like s3, but you didn't know. Okay. So you omitted S3. S3 variable was not included. Then you go to X4. X4 was not included, but there's X5 in it, and there's X's. So with such omitted variables, you are now and these are relevant variables, you are going to have a problem of heteroskedasticity. Sometimes you have to specify the model. It is a linear model, but sometimes it is non-linear model. So it requires you to use quadratics. Okay? So you have to have x1 squared. Sometimes you need to have x1 squared, x1 times x2. You need to moderate and interact some variables. If you don't do that, it means your specification is wrong. And that will require that that will imply that you're going to have a problem of heteroskedasticity somewhere. Sometimes you have to transform the variable. Sometimes there are errors. There are outliers in the model. All of these can bring about heteroskedasticity. Okay, so let's get deeper into heteroskedasticity. First of all, if the variances are constant, then there is homoskedasticity. The opposite of hetero is homo. And homoskedasticity is when the variances are constant. So you can see that it is equal to is here, equals to constant variance. But when you look here, you have not equal to is here, okay, which means that there is no constant variance. When the variances are homoskedastic, when they are heteroskedastic, the OLS estimators are still going to be linear, consistent, and unbiased. The R square is still important, but is no longer efficient. It's no longer best. The principle of blue no longer exists. Blue means best linear, unbiased estimator, and is no longer blue. In other words, there is no minimum variance. The minimum variance, the variances must be very minimum. The variability must be very little. It's no longer happening. And when that happens, in the presence of heteroskedasticity, when that happens, the standard errors will be overestimated. It's not a beta parameters. The beta parameters will still be okay, but the standard errors will be overestimated. And once standard errors are overestimated, remember, the beta parameters, you don't change it, but you can alter the standard errors, but the standard errors are bad. And remember that the beta divided by the standard error will give you the t value. Because the standard errors are bad, the t value should be bad. But the t values is what you use to get the p value. So it means that the probability values will also be bad. The confidence intervals are all invalid and biased. The R test, the F test, the LM test, the WALT test, all of them will be wrong because of heteroskedasticity. So heteroskedasticity is an issue that got to be dealt with. First, you have to check it, whether it's there. Whether or not it's there, you got to correct it. Now watch it, you got to check it first. And I say whether or not it's there, you got to correct it. So First thing is that heteroskedasticity has never been an issue to throw away an otherwise good model. According to Gregory Mankiw, 1990, it says that you don't want to throw away the model because of the presence of heteroskedasticity. So you check it, use residual plots to check the errors on the y-axis versus the x-axis. So you have the y-axis versus the predictor values of the dependent variable of the x-axis. And then you can check it. So on the y-axis, you have the errors. And I showed you some few minutes ago. On the x-axis, you have the predicted values. We want the residuals to be unbiased. We want the residuals to have a zero mean. We've checked this thing multiple times where the expected value of the residuals should be 0. So the errors are independently and identically distributed with a 0 mean, this one, and a constant variance, which is what we want. And so we are going to check some plots right now. And the expected value of the error term, that is the 0 mean error in any of the thin vertical strips you're going to see, or rectangle, in the residual plot, plus any other thing is what is going to indicate the homoskedasticity in the data. When we say that the residuals are spreading, okay, it means that they should be the same in any thin vertical strip. That is homoskedasticity. And you saw it. They should be the same in any thin vertical strip. Let me see if I can show you again. This is it. They should be the same in any thin vertical strip. Any thin vertical strip, they should be the same. Any thin vertical strip, they should be the same. It's not like that when it comes to heteroskedasticity. Okay, so let's take a couple of examples here. So in these examples, you can see that this very one here is unbiased and homoskedastic. Unbiased and homoskedastic. Now, why is it homoskedastic? Because, as you can see, if we wrap a line around this, okay, we wrap a line around this, and watch it. Okay. There is a constancy of these errors. They are not rising and and they are not increasing or decreasing. All right. And so that is why they are homoskedastic here. Now, this one, if you wrap a line around it, let me see if I can use this one. If you wrap a line here, again, you can see that it will catch this at the edges. It will catch it at the edges here. And so once again, it shows what? It shows homoskedasticity. Now, if you look at this third one, you might think that it's not homoskedastic, but when you check it carefully, okay, let me show you here. When you check it carefully, you could see that it goes, all of them goes through that edge. All of them, they go the same pathway. Okay? And then they all go the same. So the pattern is still maintained. Even though it's curving, the errors, the patterns in the error is constant. And that is still depicting heteroskedasticity. When you come to this, you begin to have a challenge. Okay, so look at this one. Consider it goes this way, so the errors are increasing. The errors are rising. Look at this. They are increasing. And in this case, it becomes heteroskedastic in that sense. And I'm just looking at the heteroskedasticity and homoskedasticity. If you look at this next one, the E here, again, you can see that the errors are rising at this section, and they are rising. It should be constant, but they are rising. That is heteroskedastic. If you look at this, it was trying to act like the previous one, okay? But you can't say that it's constant here. If you look here, it goes up, then it bends this way, you know. And then when you look at this other bit, it goes up, and then it rather comes down, unlike the previous one. The previous one was rising, this is coming down. So it's not constant. And so the bottom ones are all heteroskedastic, and the top ones are all homoskedastic. You should not have a fair idea, even if you've never learned this before, you should not have a fair idea about hetero and homoskedasticity. Now, the unbiasedness and the biasness in the data, we will not explain it here because you can't even use a graph to fully evidence. But it's the key point is the homoskedasticity here. Now, let's go to what all of these mean. And again, you can check the interpretation of each one. So if you look at the first one here, it says that the errors are equal to 0 in each thin vertical strip, and the standard deviation is the same across the plot. Those were the ones that were all homoskedastic. And then these ones are the ones that were all heteroskedastic. So you should check the interpretation. How do you detect heteroskedasticity graphically? Well, we expect non-constant variance of the residuals. Okay. If there is non-constant variance, the variances are not constant. Of the residuals are not constant. The variances of the residuals are not constant. Then you have that issue. So I'm going to take our data sets and then we go and check. We're going to show some graphs to see whether truly there is homo or heteroskedasticity in our data set that we have. And I'm talking about our Brukutu Venture data set that we have. Can you confirm if you can see the R?
You can see the R, please.
Yes, sir, I can see that.
All right, so okay. So this is a graph. I've indicated I want the graph to be 4 of these. If there's going to be no heteroskedasticity, then you should see completely random equal distribution of the points. So let's take the first graph. That is this you see on your right here. Just look at it carefully. And if you can remember what we discussed so far, you will know what we are talking about. Okay. So, flat red line, that's what you want. Okay. If we have homoskedasticity, you should see a fully equal distribution of the points throughout the range of the x-axis. Now, when you look at the range of the x-axis, and you should see a very flat red line. So if you take the first one here, it's showing both the negative and the positive residuals. Is the red line, is it flat? You can tell me. Just looking at the first one. Is it showing flat red line? You can tell. Is it showing a red first? Look at that residual versus a fitted plot. This is a residual on the y-axis. This is a fitted plot on the x-axis. Okay. Is it showing a red flat line? Flat red line? No. What you see here is a slightly up and down, rise and fall variance. It's not just horizontal. It shows some sort of non-linearity in there. The curvature with the residuals is also shown there. Look at the next one, which is a KQ plot. The KQ plot, the quantile normal probability plot here. If the dots are all seated on the line, it shows that there is homoskedasticity, but the dots, the data points are not seated on the line. So that shows some sort of non-normality of the residuals. And then look at the scale location plot. We also use that. It shows some rise and fall of the variance. Okay, if you can see the line is supposed to be flat. It shows some rise and fall of the variance, which exhibits what? Non-linearity, a sort of heteroskedasticity in there. So this will all give you a clue. That's the point. But graphs are fantastic. It's good to have a feel of the graph. But the best thing is to rather go ahead and rather test for the heteroskedasticity. Now, let me take you back to the slides and then watch the several ways of testing for the heteroskedasticity. The first one is called the PAC-LM approach. The PAC-LM approach is where you take the log of the residual square and regress that on the log of all the independent variables. That's it. Then there is a test, which is the Gleiser-LM test. You take the absolute value of the residual and regress it on each of the independent variables without taking their logs. The Harvey-Godfrey LM test, you take the log of the residual just like the PAC, but you regress them not on the log of the independent variables, but on just the independent variables. The Goldfeld and Quant test, that one is basically for cross-sectional models, okay? And you can use that. The Bruch-Pagan-Godfrey test, you take the square of the residuals, you regress it on the independent variable. Now look at that, okay? And look at this one here. Okay. You might think that is the same, but it's not the same. You take this, it's not like the Gleiser's LM test. That one is the absolute value, but this one is a square. And in both of them, you regress them on the independent variables without taking the log. The White test, okay, you take the square of the independent variables, and then you regress them on not only the independent variables, but then their squares, okay? And then their products as well. Their squares and then their products. So the independent variable x1, then the x1 square, the independent variable x2, then the x2 squared, then the independent variable x1 and x2 multiplied by each other. That is a White test. Then the Kuenka-Bassett test. You can see there are several of these. You see, the reason why I'm showing you this is I got to know that there are several of these. How do you do the test? Now, every statistical test requires that you write a null hypothesis and the alternative hypothesis. Then you document your test statistic. Then you compare the test statistic against the critical value. That's it. And then if the test statistic is bigger than the critical value, you reject the null hypothesis in favor of the alternative and conclude. These steps, we looked at them in the early days. So here, the null hypothesis is that the residuals are homoskedastic, meaning that the residuals are the same. There is no difference. All the residuals are the same and all of them are equal to 0. That is a homoskedasticity. Then the alternative is saying that at least one of the residuals differ from the 0. It's just like when you are doing a test for F test in ANOVA. If you remember that, that is similar to this. The decision rule is to reject the null hypothesis if the LM test, which is the sample size and the R square, if that LM test, which is a test statistic, is greater than the critical value, just as I indicated. And this is a chi-square distributed critical value. And then you conclude that a significant evidence of heteroskedasticity exists. That is, if the test statistic exceeds the critical value. You reject the null hypothesis of homoskedasticity, okay, in favor of heteroskedasticity, which is just like this one. If the p-value is less than 5%. So when the test statistic is bigger than the critical value, or the p-value is less than 5%, then hetero exists. That's the rule. Now, let's see in R, how do you do this test? And you will do all of these by yourself with your data. You use the Bruch-Pagan test. That's a, like I said, there are several ones, but you use the Bruch-Pagan test. This is a test. So when you're writing a thesis or a paper, you can write the mathematics formulation of the test before you show. in R. So it is a mathematical brute pagan test. Okay. Then this is a test, is the BP test function. You get that from the LM test package. So that means I got to install the LM test package first. We're going to show that right now. Now, this command will show you the LM test package, how to invoke it. So I'm going to go to my R and demonstrate this for you. So first, LM test. If you have not installed it, you go to packages, you click install, and then you type LM test. You see, it will come, as you can see down there. It's trying to pop up. And then once it comes, you install it. I've done it already. Okay, so I don't want to install. Then once you've installed it, you type library LM test. Okay, and then you run that command to invoke it. That's the first thing you do. So this is to bring it. And then you add the breach pagan into it. Okay, so now let's remind ourselves of our original data. This is original data in the results. All that we've been dealing with this past time. These were the results we had previously. And now we are going to do the breach pagan test by running this here. And watch the p-value. You can see that the p-value is less than 5%, okay, for the breach pagan. It's also sometimes called breach pagan Cook-Weisberg test. You can see that there. Breach pagan Cook-Weisberg test. So you run that. And the fact that the p-value is less than 5% means that there is heteroskedasticity. It is present. It is present in this data. In fact, the graph was showing it. It was showing it. But now we have a confirmation that there is truly heteroskedasticity because the p-value is 0, less than 5%. If you look at the breach pagan test statistic, it is 31.8. This is what you sometimes you have to bring in your data, in your result. Okay? With the 8 degrees of freedom, it shows clearly that it's bigger than the distributed chi-square critical value, which means that the p-value again is less than. And then therefore, there is heteroskedasticity. That is one. And what that means is that the standard errors will not be reliable. That's what it means. If you go and use the standard errors to get your t statistic, that will not work because the standard errors are flawed. And when the t statistic is not wrong, is not correct, then it also means that your p-value is bogus. So you cannot rely on this to use it to interpret your scores effectively. You got to correct for the heteroskedasticity that's present in the data. Okay. You got to correct it. And now, what you do is, we can check another one. Another test you can do, not only the breach pagan. If I remember, I gave you a number of them. You remember the Goldfeld and Quant? The Goldfeld and Quant, this is it. Okay. So you can run this Goldfeld and Quant here. Okay. And what that one does is that it assumes that the data are ordered. Okay. And then it will split a sample in the middle without omitting any central observations. So you can use that test to check, just to check whether what the BP test said is correct. So let's run that as well. And sometimes you get different, you know, it tells you that the alternative is that the variance is increased. That's alternative hypothesis, which means a null hypothesis. But you see, this Goldfeld and Quant is giving a different kind of assumption. So sometimes you have to note which of the tests that you want to use. And so sometimes you want to use quite a number of them to be able to arrive at a reasonable one. There are several tests that you can run. Let's check a few of them. This is, you can invoke the Skedastic, package. Okay? And then once you invoke it, like I've just done, you can do a different breach pagan test. Let's try that. And this is it. Okay? You can see that the p-value is 0, approximately. It's down here. Okay? So at least it confirms the original one. You can do the Gleiser test. You remember we spoke about a Gleiser test. Okay? That one also shows approximately 0. Confirming Cook-Weisberg test. That entails fitting the data, on an auxiliary regression. And oops, when you do that, so again, that one also shows that, well, that one is slightly above 5%. So it doesn't really come, but it's significant at 10%, but it's not significant at 5%. That is evident here. Okay. And you can compare that. There's another one that you can do by invoking the OLSRR. After invoking this OLSRR, you can also run different kinds of these same tests. So once again, you can see that approximately 0. This one is 1%. For the Bridge-Pagan test, a different aspect of Bridge-Pagan, test, when the right-hand side is set to be true, is that one is a little above 5%. And then you have another kind of test, which is 0. Okay. This one is called the score test. It uses fitted values of the model. And then you can even have the F test, which is also showing 0 value. So, I mean, generally speaking, you can use all of these tests to now make your conclusion that indeed, there is heteroskedasticity. There is a modicum of heteroskedasticity in the model. So what? So let's test it. Let's handle it. Let's deal with it. And that takes us to how to correct it. How do you handle heteroskedasticity? Remember, this one is supposed to be not equal to. How do you handle it? Well, we've already said that it can happen because of misspecification of the function, omitted variables, and several other things. Okay? All of this can happen because of that. So how do you handle it? How do you deal with it? To make it homoskedastic, you can do 3 things. 1, you can transform the data. That means that the data is linear, so you may have to change it to log linear. That is 1. The data is linear, you can change it to log linear. Because sometimes the data is not supposed to be linear because there are some factors that you have used nominal values. And so you want to use real values. And one way you can use, for example, if you are using nominal GDP and you are supposed to use real GDP or nominal inflation, you're supposed to use real inflation to reflect the purchasing power. That is the way it's supposed to go. Now, when you do that, then it becomes a challenge. Okay, so then you have to log linearize the data. Another thing is use the weighted least square, the GLS, okay, generalized least square, or the feasible generalized least square. These are some other means in which you can correct it. And then finally, you will use the white heteroskedastic standard error correction. You can use that to also correct. Now we're going to do all of these, but not all of them today. So let's go to the first one. Number 1, transforming the data. How do you transform the data? How do you deal with it? Well, the first thing you can do to transform the data is to move the data from level to log of the dependent variable. So what you are doing is that you are just converting the hill, which was hill, to log hill. Everything else remains the same. This is called log level. So our dependent variable was kill, but now we are making it a log of kill. All the independent variables remain as it is. And then you come and rerun the data and you check the result. We'll do that. If you don't understand this one, let me know. But we're going to do that pretty soon. Okay. So that is one way that you use to handle the data. But let me try and go to this and show you. log level or linear log. So let's go to the R so that I'll show you how to do that. So this is the data set. If you can remember, this was our data set. It was called gene multi equals to blah, 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 blah. But this time, watch what we are going to do. Okay, so this second one, this one. So what I decide to do is that this is the gene data, the quantity demanded. I take the log of the quantity demanded here. Okay. I take the log, I create the log of the kill, and I call it gene $log kill. That's the name I'm giving to it, and that is equal to the log of the quantity demanded. So I do that. Now, in order to see the difference, watch the kill. Sorry, the gene $kill. Okay. This is the data. These are the kill values. Wow. What I decide now to do is I've created the log of the kill values, and this is the result of that. So you can see below that each of the kill values, you change them to the log of kill. Each of the kill values, you change them to the log of kill. Now that we've done that, we have a new data set, okay, which is more or less, it's like in real terms. Then we can now come to this regression and rerun the regression. And this time, remember, I'm just using only that of the kill. Everything else here remains the same. So the model is as it was before. Watch it here. Everything is PCM lock awk rel, the same thing. But the only thing is that the dependent variable is non-log of kill. All right. I do that, and I'm renaming that model and calling it gene multi-log linear. That's all. Previously, it was just gene multi. I'm going to run this and then watch the result. Okay, so this is the data. In fact, let me just remind you of the previous one. It's too fast, so let me regenerate the previous gene multi for you. Where is the previous one? Where's the previous one? Okay, so this is the previous one. So let's compare the two. The old one is this, and you can see this old one. This is beautiful. You can see that this old one, look at the significant values. Okay. You can see that some of the variables were not significant. Now, watch this new one. Look at this new one here. Can see that almost all the variables are significant. That's the first observation that you make here. Of course, because you've changed the value of the log, because you've changed the values, what it means is that you are not going to have the very result that you would have had. You're not going to have that. What do I mean? If you look at the coefficient will not be as it was before. They will change, and the way you interpret them will also change. But the key important thing here will be in percentage terms, actually. The key important thing here now is changes, it creates a beautiful, significant result. Now, watch other things that have happened. Not only that the results are significant, but even more so, certain things are not destroyed. One, look at the R square. Let's signal out the R square. You can see them here. All right, where's that? You can see them here. Okay, but let's signal them out properly. So the R square is still good. That's it. You can see that the R square is still good. The adjusted R square is still good, like before. So it doesn't spoil anything. Now let's check for whether there is now heteroskedasticity in the model, okay, using this transformed model. By running this command, you see, this is the Bridge-Pagan test you're going to run to see if it is still present. The heteroskedasticity is still present, or it is not. Because after transformation of the model, if we check and it's still present, then we have a Wahala issue. Then we have an issue, because the thing is that we were expecting it not to be that. Okay, so let's run it and see. So you can see that after running each of the transformed model and checking for heteroskedasticity, you can see that now it is homoskedastic. How do you know that? Well, you can see that from the p-value. The p-value is very zero. This one means that there's 5 zeros before the 8, 2, 9. So there's very zero. So you can see that heteroskedasticity, what do you call it? Is now homoskedastic. Oh, sorry. It's still heteroskedastic.
Exactly.
Good. At least you are following. Okay. It's still heteroskedastic because the p-value is supposed to be bigger than 5% for it to be heteroskedastic. So it has not corrected. So we go to the next correction level. And let's go back to the slides, and then you see the next correction level. So the first correction level is this one, which I did. The next correction level is take the log of the kill, watch it, take the log of the kill, and then take the log of one of the independent variables. This is very important. Take the log of the kill and take the log of one of the independent variables. Now here, I'm doing that of the income. Okay. So I'm going to go back to the model. Then we'll look at how to handle that. So that is here, log form. So watch this very here. I decided to do for price. So I took the log of the kill, that's what you have there. And then I took the log of price alone, leaving the other independent variable. So how do you do that? Well, we've already known this. Okay, we already have this one. We already have it. We created the log of K already. But now we have to create the log of P. Now, if I run this, it won't work because I've not created it. If I run this, it won't work. It says now because I've not created it. So now I need to run it. Now I can go and show these results to you. You can see that I've taken the log of the price now. So let me now put the log of both the kill and the price into the model and then show the results here. This is it. And let me run that. And you can see, once again, it's showing significant results, adjusted, and all of those things are in order. We have to now go and check whether the heteroskedasticity is present. The R square and adjusted R square are fine. Now let's check the Rich-Pagan test for heteroskedasticity. Again, there's still heteroskedasticity. Okay. So now we have to go to the next one, which is taking the log of everything. Okay, so let's go to this third one. Okay. The third one is log. Okay. So you can see, you take the log of the kill, you take the log of the P, the log of the C, the log of everything. You take their logs. And then you run and you check. Let's see. So here I called it log. Now I already have the log of the K and the P. So I need to generate the log of the C. I need to generate the log of the N. Okay. Now, we don't do the log of the dummy variables. Take note. We're not taking the log of the dummy variables. And you run it. I call the model log. And this is a model. I run it. Again, this time, some of them are not significant. So that we go back to the original. Some of them are not significant. Let's check the summary of the R squares and adjusted, they are all fine. Let's check the Rich-Pagan. It is still exhibiting what? Heteroskedasticity. So,
Yes.
and I've seen this already. So what you will notice is that heteroskedasticity was not handled by log transformation of the model. What do you do now? What is the next thing you can do to deal with the situation? Well, there's another approach you can use. And it's always good to always compare the model. Okay? It's always good to compare the model and then determine which one is the best. You see, by going through this model, I would have created a table for each one of them because you've suffered. You've gone through the model, so you are supposed to show the model in the thesis or in the paper to let the reader know. So sometimes when you read some papers, you will have model 1, model 2, model 3. And I'll show some of them here very soon. And the reason is because the model 1 contained the log of P. The model 2 contains just the log of Q. Model 3 contains the log of P and log of Q. Model 4 contains the log of all. And you show all of that. And that is good when you are able to show all of this in that regard. Now, let's go back to the slides and look at the second way of handling heteroskedasticity. We said that heteroskedasticity can be corrected using the log transform model. We've done that. We didn't get anything. We've got to go through the next one, which is a heteroskedastic, white, robust heteroskedastic standard errors. So this means that we're going to correct the standard errors to see that heteroskedasticity is handled. How do you do that? Now, here's the thing. When there is heteroskedasticity, the OLS estimators are not blue. We've said that. Okay? They are not efficient. And you can use something called white heteroskedastic corrected robust standard error, okay, pioneered by White in 1980. And if this can be performed to be able to validate the result, but the results is normally good for large samples. And the robust standard errors sometimes is also called the Ica-Huber-White, okay, because of the later expansion. These standard errors are larger than the normal OLS standard errors, which would then give you lower p-values for the independent variables. But in reality, we don't test for this heteroskedasticity in real life. In reality, we just report the standard errors. Okay? The heteroskedastic standard errors, the robust one, we report it without necessary testing. You cannot implant it into the estimation. That is what we are going to do. Apart from that, robust standard errors, there is another one which I love the most. It's called the Newer West standard errors. Now that extends the white one. Remember this, don't get confused. The coefficient is normally first, is the estimate. Then you have the standard error. When you divide the coefficient by the standard error, you get the t statistic or the t value. Then from the t value, you can get a p value. The standard error here is what we are trying to correct. You are correcting that standard error so that when you divide the coefficient by the new standard error, you will get a higher t statistic and a lower p value. That's all we are doing. The Newer West standard error will extend the white one by dealing with autocorrelation as well. So it's not only dealing with heteroskedasticity, but autocorrelation. We'll look at autocorrelation next time. But strictly speaking, when the samples are large, okay, that is when these tests are very, very beautiful. When the sample is small. Now the question becomes, how large is large? If you have only 15 to 20 observations, the sample may be small. But if you have, say, 50 or more, then the sample may be reasonably large, but more is always better. So you can't go and use it on a small sample and still say that, but it's still a problem. And guys, remember our sample. Our sample was 40, if you can remember. Do you remember? It was 40 observations. So with 40, that is why we are having multiple issues of heteroskedasticity in the data, in the results. So again, if the samples are large, Now, how do you enlarge the sample? Simple, collect more data. You remember we are dealing with cross-sectional data. So if you collect panel data, so you don't deal with only 1 year data, you deal with 2 years, 3 years, 4 years. So that tends to increase the sample. And as you increase the sample, you'll be able to handle this issues effectively. Okay, so let's go back to the R and go and check. Even though it is still a bit of a small sample, but at least it's reasonably bigger than a small sample. Let's go and run and use this second approach of dealing with heteroskedasticity. First, you have to invoke your scoring package, invoke your LM package, invoke your sandwich package, and you do all of that. Once that is done, you use this command to run the white one. So we're going to do the white one first. And the white one, the type of the heteroskedasticity, the last time I spoke about it, it can be HC, H1, HC1, HC2, HC3, all the way up to HC5. There are many types of the robust standard errors from HC0 all the way to HC5. Okay. So you can do that. So let's run this one and see. So again, when I run this one, you can see that all the independent variables are heteroskedastic. You see, I have not changed the model. I have not transformed the model. The p-value, the price is still negative 3.15. It hasn't changed. I've not logged, linearized anything. And still, this time, you can see, if you compare this with the previous one, let me just show you the original data. This is original. Now compare the two. You can see that the original one had 2 variables, M and log M to be insignificant, but they are now significant. One at 5%, one at 10%. So again, you got some significant results. Now you can use the HC1 to check. This is the HC1, it gives still significant results. And that is it. Now, ideally, once we are done, we have to check. So remember, what we've done here is not to test for the presence of heteroskedasticity here. What we have done, or we are doing, is that we are correcting for the heteroskedasticity, straight away, to be able to now use, because it's not, our interest is not heteroskedasticity. Our interest is the p-values, to make sure that they are significant enough for the purpose in which we brought them on board. And you can see clearly that they are, especially the first one. There's the first one. There's the first one here. It's very much significant here. But I'm more interested, like I said, in the newer West. And this is the newer West standard error. Remember, I indicated that one not only correct for heteroskedasticity, but also autocorrelation. So it is solving 2 problems. And that means that if the 2 problems are there and it does solve them, then you're going to have a beautiful, significant outcomes. Okay. It uses something we call Bartlett kernel with non-parametric bandwidth selection. When you get a paper, please read it. You are West, 1987 and 1994. Okay. You do that. So this is a command that does that work for you. Let's run it and see the result. Okay. So I've run that. Yeah. You can see the results by just running this. Okay. Because remember, it's the standard errors we are interested in. So this is it. And you can see the results are all significant at 1%. That is cool. Okay. Now, in order to get this whole thing, let's put it all together in a stargazer, a beautiful data, a table, to get the picture and understand the comparison. So I'm going to generate a stargazer. Again, you have to install and invoke stargazer library from the library. I've installed it already, so let me invoke it. And then you can now generate your result. Watch the results I'm trying to generate here. Let me just come here so that you can see all of them. You'll appreciate it even more. Show you something. See what Stargazer is doing is that it's trying to put everything into a table. Okay. So let me just move this one. to the left. So watch it. Stargazer is first showing you the original regression model. Then the regression model that has the log of the dependent variable, the second one. Then the regression model that has the log. I don't know whether we ran that one. Then the regression model that has the log all. Then it has the newer west. I didn't want to do the white one. Decided to do only the newer west. Okay. And now you have to give the names of it. So the first one here, the gene multi, his name is OLS. So I call it OLS. The second one here is log linear. Okay, so I called it log linear. You have to name them and put them in double apostrophe. The third one is a log. That this one is when the dependent variable alone is log. This one is when everything is log. And this one, no, the log is, I think, I hope I ran that, because if you didn't run that, it won't show. And then the last one is when everything else is log. I would call it log all. And then the very last one, the newer west, okay, I called it robust SE. But from what I'm seeing here, we are supposed to give this name to it. Okay, so let me change it and call it robust newer west standard errors. Robust NW standard errors. Okay. And now I indicate that I want the R to give me some important information. I want the sample size to be shown. I want the R squared to be shown. I want the F test, the log likelihood, the KK information, the BIC, the log likelihood ratio, the wall test. If any of them has it, you want it to be. So let's run this table and see what happens. Okay. So I'm told that the space is too small. So we're gonna run it again. Yeah, sometimes it won't show, but let me see why. Because if it doesn't show, it means that you have relabeled something. So I need to be sure that the gene multi log, I ran it. What is a log? Gene multi log. I think I did. And then it must follow in that order. So we have gene multi log linear. Okay, so I need to go and check whether we did gene multi log linear. This one. Yeah, we did it. Then the third one was gene multi log. Gene multi log. This one. And then we had gene multi log. So we had all of them. Let's see. OLS. So the first one we called it OLS. The second one we called it log linear. The third one log. The fourth one. Then let me just close this with that. So sometimes when you run these things and they don't work, you don't have to be worried. You just have to double check to see whether you made any mistake or what. Okay. It still says that, is it because of my space? Let me check. Oops, I went too far. All right, so I think, let me just run this again and see. It's not available. Let me see. Something is just not showing well. Other than that, all I have to do is to just change this one to that. Keep straight. And then But I've done it already, so I'll show you the results. For some reason, I'm not getting the table popping out nicely, but here it is. Just because of time. By the way, where is my table? There's it. Okay. It might not even be bigger here. Let me see. So the table will look like something like this. Sometimes you have to add a couple more. But this is it. Let me see what we are missing. I think gene multi. We didn't do this one, so we'll hold on to these two here. And then we had gene multi log linear, gene multi log, and then robust. And then column dot labels, and then the following. So let's just go back and see. Sometimes it's just a small, tiny thing that you have to. So you have log underscore linear. Log underscore linear. So where is that one? Looks like, hold on. Gene multi underscore log underscore linear. Gene multi underscore log underscore linear. Then gene multi underscore log log. That one. That one. That last one. 1, 2, 3, 4. Honestly, we got all the key things that we needed to have. Column, dot labels. Sometimes it's because of my space that I'm having, which it says an error in if it's not available, the condition has been. I just, and when you encounter some of these, that is when you know that you are learning, by the way. It just shows that you are really learning.
Yeah. We are facing similar in the assignments.
It's good.
No.
Yeah, we all face that. It's normal. So I'm trying to see how you fix it. And one way you fix it is to use if-else function. By default, that if-else function will check the element in the vector at one time and will allow you to avoid the error. So how do I use the if-else command? Let me see. Okay. Yeah, I think something, it's a very tiny thing. I think because of the timing here, that is why I am, the condition has learned greater than 1. Can you count this? 1, 2, 1, 2, 3, 4, 5. 1, 2. I'll take this one off. So it's 1, 2, 3, 4. Yeah, it's the same thing. Okay. Hold on. And the column labels are there. Then we should have keep dot starts. Sorry. So you can check it. Now, when I do it, I'll let you know so that you can get it. It will produce a beautiful table like this. Let me try to show you. A beautiful table similar to this, just like the one here, I added more. And that table, and you can see at the table. So sometimes you have these things. And this is the first one. That shows the OLS. You see, the logs here were not part of that. So they are not shown here. Then there was other models, and I'm jumping these two. Then the log linear, that is it here. Then the log, that is it there. Then the final one, the newer words, I changed the name here. That is it there. So you are able to now compare this. When you go to the bottom, you will know some other information of that. For example, the observations are 40 for all of them. So that is there. The R-square for each one of them is also there. And then the log likelihood is showing for some of the models. But for some of the models, you need log likelihood. And as you can see, the ones that have the log likelihood are just the GLS. I'm wondering whether that is why maybe this one is not giving us because of the log likelihood or not. But it will have these things. If it's there, it will show. If it's not there, there is no need. We'll try something just quickly and see. Oops. So you have all of these showing, and then they help. The good thing is that they help the person to be able to know where it's going. Anyway, so remember that my interest is in the last one, which is a newer wedge, which automatically solves. Now, in the table, the coefficient is what comes first with a star, whether it's significant or not. Then what is in the bracket, you can choose whichever one you want to put in the bracket. You can put the p-values in the bracket, or you can put the standard errors in the bracket, whichever one you did. But this ones, those are the standard errors in the parentheses in the bracket. And then that will help you to be able to know exactly what you are dealing with. Remember that we have corrected the standard errors in the last one, and the last one promises to be a very good one. Okay, so the second way of dealing with let me just go back to the previous one. The second way of dealing with heteroskedasticity was not to transform the model, but to handle it straight on. That's what we're doing. Okay, you handle it straight on. You generate the heteroskedasticity and handle it straight on. I want to go to the very last one, and then we are done. Okay, the very, very last one. And let me just go to the slides now. So let me just go back to here. So the first one was to transform the data. We looked at it. The second one is to use the white robust test, which you now know that you can also use the newer West test. Newer West, robust standard errors to correct for the standard errors without even testing, like we said. And then the last one is to use a different model to deal with the situation. And this is weighted least squares or generalized least squares or feasible generalized least squares, which happens to be the weighted. So we're going to look at that. It's very, very simple and just a little bit of math in it. And here it is. This is the weighted least square. Let's start with that. The first way to handle heteroskedasticity, you see, these ones are handling the heteroskedasticity straight on. How do you do that? If the heteroskedasticity is known, then the weighted least square can be used. And you use that through a function in R called GLS function. Or you can use feasible GLS. We'll talk about that. That's if the heteroskedasticity is known. But if it is not known, if it is known up to a multiplicative constant, which means that it is known in such a way that you can multiply the variance by a certain factor, multiplicative factor. Okay, then we can do the following. We can use this to transform the entire regression model. We can estimate the transform model this time by OLS because we've transformed the regression model. And now we don't need to do anything, just estimate the transformed model by OLS. And how do you transform the model? We multiply the errors by the factor. The factor is 1 over the square root of hi, which is that constant value. Or sometimes you don't even want to use the square root, you can just do 1 over hi. And this will make the residuals homoskedastic. So how do you do that? This is how you do it. So your model is there, you take the variance. So first it was variance of ui, right? That's what it was. Now you make it variance of ui over the square root of I. What we've done is I will multiply the ui by the 1 over the square root of hi. So the ui go to the top, the numerator. So we have ui divided by the square root of hi. And when you expand, you are going to have 1 over hi multiplying the variance of the ui. Okay. And the variance of the ui, we know that to be what? We know that to be the heteroskedasticity, that's the sigma square. And since this one has a square root, okay, when you take the square root, and because the sigma has a square already, the square, when you multiply both sides by squares, the square root will cancel the square. And therefore you will have back, I mean, you can see it here, h will cancel, and then you have back the sigma square, which means that now we are back to homoskedasticity. This is what called transform. Now you are going to estimate the transform model, the one you did, you're going to estimate it. This is a second approach. The same thing, you multiply it by 1 over the square root of hi. You multiply that through the dependent variable and then the independent variable. Each one of them is multiplied with 1 over square root of hi. And when you do that, watch, you now get new dependent variables and independent variables. And you will have an error term as well. So in this case, the model now becomes what? Heteroskedastic, homoskedastic. But if the model has homoskedasticity errors, if the model is heteroskedastic, the third approach you can then do is you can use the OLS approach on the transform model by, again, multiplying it by 1 over the square root of hi. This becomes like the weight. I'll use this one very soon. And when you do that, you are going to have the WLS or the GLS, which means it has a weight. In the WLS, the observations with a higher error variances have less weight. The OLS can now be used on the transform model. Remember, the OLS estimator is this. We know this from the long time ago derivations. But this one will now change to GLS. The beta will change because now we have a GLS, which eventually becomes that. Now, this can be proven easily, where the omega, is the summation in real life. And then you can now find that the variance of the beta was this. This one, we proved it, called error demonstratum. And therefore, you will now have the variance of the GLS, the beta GLS, to be that. This beta GLS is no longer, unbiased. Is now, no longer biased and no longer inconsistent. Is now unbiased and consistent. Even in the presence of heteroskedasticity, that's it. Even in the presence of heteroskedasticity, we've solved that situation. Now, there are differences in the assumptions about the errors and the variances. And so sometimes you have to choose between the GLS we just showed and then the OLS. Okay. And choosing the GLS over the OLS is to gain asymptotic efficiency, is to ensure consistency, smaller variances. And it's easy to get the GLS estimate, even when you have heteroskedastic errors. And note that in GLS, we divide through by the standard deviation, similar to the WLS. In the WLS, we multiply through by 1 over something. They are synonymous. Sometimes they are synonymous, sometimes they are not. Finally, the feasible GLS is just an applied version of the GLS. That's how I will call it. That is when the heteroskedastic form or the structure is unknown. The best way to understand this is showing these results. And again, you can try it on your own. Okay. So I'm going to go finally to the and show you how those ones work. So I'm going to do the weighted least squares one. Watch what I'm doing here. The LM, Q, PCM, all of them are there. Then I introduce a weight. Okay. And I call the weight 1 over C. Now remember that C is one of the independent variables. I use it as the weight. And then I run the model. Watch the model. This is it. Everything is significant. It's a beautiful way. So what you've done is that you have converted the information and you've still been able to achieve. You divide, you introduce a weight, that's a weighted. You introduce a weight that is applied to the independent variables and that of the dependent variable. And now we get this estimate. And you can see one good thing is that this estimate, not just the standard errors, and then the p-values are beautiful, but also the estimates. See, previously we had negative 3.15, now we have negative 4.26. So you can now beautifully interpret the results the way it's supposed to be. Another way is by using the GLS. This was the weighted least squares one. You can invoke the library command, which is known as the nonlinear model. Remember, we always talk about the linear models. Okay. And then we do the GLS. And then the errors here, we allow them to be correlated with the unequal variances, the one I explained in the slide. You create your gene multi and then call it GLS. This time you don't use LM in front, you use GLS in front. Everything else is as it is. You are running the whole model by the GLS. This is how it goes. So the GLS, you see that one, what it does is that it gives you these fitted statistics, the Akake information, the BIC, the log likelihood ratio, all of these things you have to learn them separately. Then you're able to get these. And these results, this p-value will tell you whether it's a star or it's not a star. Okay. And to be honest, from what I see here, it's not even better. It's just like the old one that we had before. So we can go to the feasible GLS. The feasible GLS alters the GLS a bit. To do the feasible GLS, what you do is that you obtain the errors of the OLS if there's heteroskedasticity. Now, these are the errors. The residual, let me show you the error. These are the errors before I change it. Okay, these are the errors for each observation. Okay. Let me run this and then show you the same errors now. Okay, so these are the errors. I now take the square of the errors and then take the natural log of the square. So I'm going to take the square of the errors. This is the square of the errors. And then I take the natural log of the square. Now watch it, negative 1.699. If you square it, you get positive 2.88. That's the square. Now I take the log of the square. This is a log of the square. This is a result you are seeing here. Okay, negativity is removed. Now you regress the residual squares on the independent variables. So these are the independent variables. I take the square of the residuals that I generated, I regress them on the independent variables like that. Okay. What do you get? You get this result. Now this result might not make true sense yet. Okay. Then what you do is that you now have your fitted values. Okay. You generate the fitted values from that regression. This is the fitted values. Let's rename it as 1. And then you can now exponentiate that y hat. If you go through this, they are very simple. And when you exponentiate the y hat, this is what you have. Now, see, at this stage, you can create the weight and re-estimate the model. This is the feasible GLS. So let's call it. So this feasible GLS is that YH hat that we had. That's what is going to be our weight now. And this is it. See, we have a beautiful results all shown here. Watch the p-value. I mean, watch the p-value. They are all significant. Okay. And then watch price. Price is now higher, and it is showing a beautiful negative relationship between price and quantity demanded. Now, this was the original one we had. This was the original one we had, previous one. And when you compare that previous one, the one where you chose the C to be the one that is used for the weight. Okay, this is it. You can see that C and M are significant at 5%. Yeah, they're significant at 5%, but here they're significant at 1%. And this is the other one, the old one that we had. I'm adding the old model, the one with the log. And then the gene multi, the one with the log all. And then the robust new OS, I add that one as well. And now, let me see whether this, watching this table still didn't show. I think we have to check that. And you can generate the beautiful table that we have there. So the key point you want to take from this is that heteroskedasticity can be handled by these three approaches: transforming the model, using the white robust standard errors or the West standard errors, or using feasible weighted least square, the generalized least square, or the feasible generalized least squares. These are the ways you can use to handle all of this. There are several things that one can do. For example, these are some of the ways you can generate your weight, and handle most of these, and then finally come out a beautiful model of that sort. All right, so let me just go back here. I've put all of this together in the slides, and you can see all of this. And the most important thing is now, even though you would have used different models, don't say that when you are presenting your model, show all the worries you went through. You went through a lot of worries before you came out. So show it. This is the OLS you generated. Show it. This is a GLS you showed. Show it. This is a feasible GLS you had. Show it. This is a weighted least squares. This is a log linear model. This is that. This is that. This is a, show it all, and then decide to pick the one that you feel it explains your point you want to make based on handling your issues you have. And then use that one to now conclude and discuss all of your results. Okay. But the way you interpret them also matters. Okay. So for example, if I use a newer West here, which is what I would have used, I'll use that and then use it to interpret all my analysis. And it fits into all of them. So the R square is still beautiful. Then you can now, but you show these ones. You show these ones. Where there are dissimilarities, you now use a particular model that solves that dissimilarity that you want to actually do it. And then that will be it. Okay. So this is how you handle it. So let me tell you one last point on feasible GLS. Under the feasible GLS, it becomes an indicator. It's important to know that when you're interpreting the feasible GLS, you have to be careful because the slope coefficient used as the weight becomes the intercept of the model. And we've indicated that you can use a feasible GLS to produce a homoskedastic error, an error that is no longer heteroskedastic. We've said that already. And then you have this final point that instead of the feasible GLS, you can just use normal OLS and correct for the heteroskedasticity straight away using the newer West, just as we did as well. And you've got some references here. The newer West paper is here. It's published in beautiful econometrica. And look at it. and feel it and enjoy it. And when they tell your friends that you did it, you looked at it, that is how you do it. So, ladies and gentlemen, that brings us to the end of the entire caboodle. Next time, we'll look at autocorrelation, the final one on the head, on the robustness, the diagnostics. And then after that, we'll start panel data econometrics. That's it. Have a good time.